once again welcome to this lecture. We have just completed the various aspects of permeability and seepage related issues, and in the meantime we have shown derived different things particularly for determining permeability, for calculating equivalent permeability, and then flow through the dam structure and all below the through the body through the below the dam through soil obviously. And then I will try to take a few problems now that to apply those one by one. So, I will just take the problem number 1, application 1, that is the results of a constant head permeability test in a fine sand are as follows. Area of the soil sample is 180 square centimeter, length of the specimen 32 centimeter, and constant head maintained during the test is 46 centimeter. Flow of water through the specimen 200 milliliter in 5 minutes. So, based on this given information, you have to find out the coefficient of permeability. So, this for this actually what we can do, I have discussed before that how we do the this test. We do the test and suppose this is the soil sample and your quantity of seepage is collecting from here, and in this we have the different dimension. This is the length of the soil and flow taking place for water. Actually, your head difference because of which water is flowing through it is a h, and your quantity collected suppose q, and cross sectional area suppose a. Then this is the test procedure. That means you are constantly supplying water here and maintaining the height here. So, that if goes more, if comes more than more water comes here, it will come out through overflow maintaining this height, and this is the sample through which it is continuously water, and water then flowing through this and finally coming out here, where over a particular time t we have measured the quantity suppose q. In that case, this is the equation. So, q actually you have 200 q is equal to 200 ml equal to 200 centimeter cube, that is called capital Q, and A area is given 180 centimeter square, and H equal to constant head 46 centimeter over under which flow is taking place, T equal to 5 minutes, and your L is equal to 32 centimeter, and our equation, governing equation, K equal to Q into L by A T into H. So, all those quantities are known here. So, if I substitute all of them, so 200 and multiplied by L equal to is 46 no L equal to 32 and divided by area is 180 and T is 5 into H. If I do this, then I will get 0.154 centimeter per minute, and which will be equal to 0.00 258 centimeter per second. So, this is the thing asked in this, that means given condition in a constant head permeability test, quantity collected over 5 minutes time at 200 ml, and the test was conducted on a sample whose cross section area is 180 centimeter square, and length of the sample was 32 centimeter, and head difference because of which flow is taking place, that was actually 46 here. All those things are given, I have just substituted and get the value k. Now, let us go to the second problem, that is your application 2. Compute the coefficient of permeability of soil on which a falling head test has been carried out. Area of sample, again area of sample 80 centimeter square, area of standpipe for 4 centimeter square, and length of soil sample 15 centimeter. Time versus head difference readings are as given below. That means, what is given here, at time 0 head was 107, at 27 minutes, after 27 minutes head was 105, after 60 minutes is 103. These are the readings taken. So, based on these readings and based on this given and given in the information, that means sample dimension, area and length, and the water is applied through a standpipe, the standpipe cross sectional area also given, and based on this we need to find out the permeability. So, this is a falling head permeability, that means what, the head initially kept at some level, and then after some time because of the flow taking place, the head is coming down, and so that taking this observation, how much time taken to drop the head from H1 to H2, that to be considered in calculation. So, if I do that, generally our test procedure is something like this. There is a something like this sample will be there, and sample may be some, this is the sample suppose, and this may be something, and through which there is a standpipe, suppose this should be uniform section, obviously is not as I have drawn here. So, if it is sorry better so standpipe is somewhere something like this, and water is kept here, this is water, and this is suppose water is collected from here. Generally, this quantity of water collected is not necessary to measure, only thing is required to see the head difference. So, suppose initially head was somewhere here, and after some head has come down here, and this is the cross sectional area A, this is the length L, and so and head H1 to H2, there is a time. So, this to be considered, and our equation for permeability actually Q1 equal to A times L into ln H1 by H2 divided by AT. So, this is the area of standpipe, this is standpipe cross section, and this A actually area of sample, and this is a time over which the head drops from H1 to H2. So, there are three combination we can do. I can consider K1 first. K1 meant, that means after 27 minutes there is the head change from one head to another head, that means so that if I put, so that is 105 to 103, sorry this was 107 to 105. So, if I put that, the cross sectional area of standpipe is 4, length is given 15, and area of cross section of sample is given 80 and time is actually it is 27 minute and ln 107 by 105. So, that means I have 2 times interval is given and 2 different heads are given. I am taking 0 time to T1. So, that I am representing as K1. If I take this one, then it gives you a value 0.0000524 centimeter per minute, and if I consider it will be 8.73 into 10 to the power minus 6 centimeter per second. And previously we have got for sand the value was quite high and it is actually falling head we do generally for fine grained soil where permeability is low. So, this permeability also showing quite low value. Similarly, I can consider K2. K2 is what? Actually, I consider the observation between 2 and 3, that means at 27 minutes what is the reading and your 60 minutes what is the reading, this difference of these two. So, this quantity will be same 4 into 15 divided by 80 into 27, this will not be 27, this will become 60 minus 27. 60 minus 27 and this will be ln, this will be 105 was there at 60 minutes and at 27 minutes and 60 minutes 103. So, this if I do this gives you the K value 7.28 into 10 to the power minus 6 centimeter per second. And now, I can do another that is K3. K3 how I can take? I can take observation 1 at 0 time and at 60 minutes time. This if I do, then it will be 4 into 15 divided by 80 into 60 now directly at 60 minute time I am taking reading and ln will be initially was 107 and finally, it become 103. So, this one. So, I can get another value of permeability K3 that is actually 7.93 into 10 to the power minus 6 centimeter per second. So, whatever range of values I have got 8.7, 7.2 and 7.9, they are actually in the permeability it changes in 10 times or 100 times. So, because of that this variation is reasonably within the range and because of that we have got 3 values, but I can finally recommend the average of this, the K will be equal to K1 plus K2 plus K3 divided by 3. So, that if I put that one, that gives you 7.93 into 10 to the power minus 6 centimeter per second. So, this is the one. So, main application is one, this is equation, main application of the this is here actually using this equation, that is A L ln H 1 by H 2 by A T, where small a is the cross section of the standpipe and capital A is the cross section area of the sample and T is the time interval over which the head drops from H 1 to H 2, and what is H 1, what is H 2, that to be observed. If I do that, we will get the value of K. Since there are 3 sets of data observation is given, we can calculate 3 K 1 value K values and average of these 3 can be reported as recommended value of K. Now, I will go to application 3. This is actually for a field permeability test by pumping out. That means, the pumping out test is a field test, that we make a borehole first and through that borehole we will by using a pump we take out water, and the quantity of water when it become almost constant over that means steady rate, and that is one thing to be observed. Another thing is at some distance from the main well there will be some observation well, and that observation well also we have to see how much is the drawdown. Drawdown it will not be the same as it is in the well. If you go away from the well, your drawdown will be reduced. So, that application is shown given here. For a field permeability test by pumping out, a well was sunk through a horizontal stratum of sand 15 meter thick and underlain by a impervious layer. Two observation wells were sunk at horizontal distance of 15 meter and 35 meter respectively from the pumping well. The initial position of the water level was 2 meter below the ground level. That means, water bearing layer, the sand layer thickness is 15, but water was there only 13 meter. And after a steady state pumping at a rate of 925 liter per meter, the drawdown in the observation wells were found to be 2.5 meter and 1.5 meter 3 meter respectively. So, based on this observation, we have to find out the coefficient of permeability of the soil. So, generally what is the thing we do? Our typical pumping test schematic diagram is something like this. Is suppose the pump, and there may be some impervious layer, and this is the ground mark suppose, and water layer is somewhere here. So, this is the water layer, and since total is 15, so this depth will be 13. Now, observation wells are here, one, another one here. So, this distance of observation well, one is 15 meter, another is 35 meter. And when you do the drawdown pumping, you do the pumping, then it drawdown will be something like this. So, here draw down something, here draw down something else. So, based on the given information, this is actually your 11 point, this become 11.7 and this become 10.3 and this is 13. So, your H 1 equal to 10.5, H 2 equal to 11.7, R 1 equal to 15, R 2 equal to 35, and if you have Q equal to 925 liter per minute equal to 925 into 1000 centimeter cube per minute, and if I do that, then our expression is K expression equal to Q into ln R 2 by R 1 pi H 2 square minus H 2 square minus H 1 square. So, all the values are given here. If I substitute in this, all the values are given. If I substitute in this equation, finally, we will get a permeability value equal to 0.0156 centimeter per second. So, in this problem, of course, in this problem again I have mentioned while discussing this, I can find out what is the area of influence. That means, by what distance there will be no drawdown. So, once you get the K, and using this I can find out that also. So, one I will consider at a distance r, the drawdown is 0, that means observation is one reading is H 2 is 13. So, that using that one can find out the other thing also, means distance at up to which there is no drawdown or influence area you can say. So, that was the application 3. Now, I will take one more problem, that is application 4. this is the application 4, and so here actually a bed of sand consists of 3 horizontal layers of equal thickness. The magnitude of the coefficient of permeability of both the upper and lower layers is 4 into 10 to the power minus 4 millimeter per second, and for the middle layer it is 6 into 10 to the minus 2. That means, the permeability is high. That means, there may be 2 clay layers and top and bottom where permeability is low, and in between 2 layers there may be a sand layer where permeability is very high, actually 10 to the power minus 2 and 10 to the minus 4, that 100 times. So, in this case when flow is taking place, how to calculate actually. So, that we have to use equivalent permeability concept. So, when you apply equivalent permeability concept in vertical and horizontal direction, it will be different, and that is what question is asked, what is the ratio of the average permeability of the bed in the horizontal direction to that in the vertical direction. So, average equivalent permeability in x direction and y z direction will not be same, that will be different, that we have shown while discussing the topic. Now, we will show that part in the application here. Oh, sorry. So, suppose there is a 3 layers as it is mentioned, one here, one here, one here and one here. So, 3 flow can be taking place in this direction and flow can take place in this direction, and you can say that the 4 into 10 to the power minus 4 here, 4 into 10 to the power minus 4 here, and whereas here 6 into 10 to the power minus 2, and whatever value is given, assuming within that layer it is isotropic, that means both k x and k the both the direction it is same. If I consider that, then in thickness, all the thickness suppose h, h and h, then in horizontal direction we can k e x, suppose our formula is k 1 x h 1 plus k 2 x into x 2 plus k 3 x into h 3 divided by h. So, if I apply this, that means all h 1, h 2, h 3 is actually same. So, it will be coming h, and actually you can say 3 h, sorry, this is h and this is h plus h plus h, this total h actually. And so, here actually h 1, h 2, h 3 will be if I consider h 1 equal to h 2 equal to h 3 equal to h. So, in that case it will be h into k 1 x plus k 2 x plus k 3 x, and here actually total thickness of height, that means h 1 plus h 2 plus h 3. So, it will be 3 h. So, h get cancelled, ultimately it is nothing but the average of the. So, when your flow is taking place in horizontal direction, then it equivalent permeability is nothing but average permeability of the 3 layers. So, if I do that, then you see it will become it will be 4 plus it will be 600 plus 4 into 10 to the power minus 4 divided by 3, and that become 202 into 10 to the power minus 4 millimeter per second. Okay. And whereas in KZE, when it is vertical direction, when you consider, there actually it will be h 1 plus h 2 plus h 3 divided by h 1 by k 1 v plus h 2 by k 2 v plus h 3 by k 3 v. So, since they are all equal, so we can, this equation can be ultimately converted equal to it become ultimately 3 divided by 1 by k 1 plus 1 by k 2 plus 1 by k 3. So, k z become 3 divided by this, and if I do this, finally, your k z e become 5.988 into 10 to the power minus 4 centimeter per second as it is given. And now, if I do ratio of horizontal k x e divided by k z e, then it different, this ratio will come 33 times. So, this is another, that means simply I have to remember when horizontal direction flow, this is the equivalent, when vertical direction, this is the equivalent equation. This equation if you remember, rest of the things are nothing. So, I will go to the next application. So, question number 5. In this actually you can see the application is given a flow net, application of flow net. A flow net around a single row of sheet piles in permeable soil is shown in figure, given k x y k equal to 5 into 10 to the power minus 2 millimeter per second. Determine how high above the ground surface will the water rise if measured by piezometer placed at points A, B, C. That means A, B, C is shown here, A, B, that means at this point, and C is at this point. What will be the rate of seepage through the flow channel per unit length of the sheet pile, and what is the total rate of seepage through the permeable layer per unit length. So, this is the question. So, you can see that there is a how many flow channels, one flow channel, second flow channel, 3 flow channel I can consider. How many drops? 1 drop, 2 drops, 3 drops, 4 drops, 5 drops, 6 drops. So, 1, 2, 3, 4, 5, 6. So, number of drops 1, 2, 3, 4, 5, 6. So, N d is 6, N f is actually 3. So, these are the observation we can see from this diagram, and as it is mentioned that since this is at equipotential line, this point actually one drop only taken place, and the head is total actually 4.5 to 1.5, that means 3. That means how much is the head loss from going from here to what? 3 meter, and 3 meters is losing over a 5 drops, 1, 2, 3, 4, 5. This is one, so 1 drop, 2 drops, 3 drops, 4 drops, 5 drops, 6 drops actually, 6 drops actually is there. So, that means each will be 3 by 6. So, so 3 by 0.6. So, that way I can find out if I know that. So, that means in each drop actually this much. So, it was here 3. So, here it will be 3 minus this much. So, that is the one. So, if you go to B, then 3 minus 2 times this, and when you go to at point C, since again how many 1, 2, 3, 4, 5 drops are there. So, H minus 5 into this to be calculated. So, that means, if I put a here, then different. So, let us see that how to do the calculation. So, here actually del H actually I have done del H equal to 3 by 6, since it is 6 drops are there. So, whatever value it comes at A will be equal to total head actually equal to 4.5 minus 1.5. So, it is 3. So, at A it will be 3 minus 3 by 6, and at it will be B equal to 3 minus 2 into 3 by 6, like that. Similarly, at C also you can find out, and also at D point, and Q will be equal to K into H into N f by N d. So, K will be given, K is given, and H actually is 3. So, K into 3 into N f actually 3 again, and N d equal to 6. So, by doing this calculation one can find out the value of permeability I mean water, how much water is passing through this structure. So, this is the 5 application I have done. Still one or two may be required. So, I will do in the later sometime later, maybe in the next lecture. So, with this you can conclude permeability and seepage for the time being. Thank you.